Good afternoon. It's almost 3 o'clock, so qualifies for afternoon. I see some faces from the SSIS session we had this morning, so the data warehouse trip continues. Never ends, actually. This afternoon we're going to, for the people that didn't see me this morning, my name is Nicolas Dritsas. I'm a principal program manager with the SQL Server team. And I'm part of a smaller team. We call it a customer advisory team. What we do, my team, is we work with the most challenging, bleeding edge, big, ugly SQL projects in the world. Hopefully we'll make them better. The idea is, we're learning a lot from them, make the product better, and mostly share with the community lessons learned, best practices, so you don't do the same mistakes we did. So today we're going to discuss a topic around FastTrack and parallel data warehouse. Actually, it's an introduction to parallel data warehouse, since we don't ship that product yet. Well, almost, but it's not available yet. Out of curiosity, does anybody know FastTrack? Has done some research? What is that? There's one. Nah. This is an interesting classroom to go like that. Okay, good. So I guess there is some work to do to discuss what FastTrack is and all that. So it will be a good session. All right, so this is the agenda for today. We're going to discuss. Actually, I want to give you a little bigger picture. Microsoft today has 3-4 offerings around the data warehouse area, and we can discuss which one potentially can fit you based on the data size or the complexity of your data warehouse. We'll talk a lot around the FastTrack offering because that's the main topic of the conversation, around what motivated us to create this architecture, especially around the balanced architecture. We'll talk for examples, and we'll talk for a couple case studies that we have done with some major data warehouse systems. And at the end, we'll talk for the parallel data warehouse offering. We'll do a small overview. That gives you kind of the next steps where Microsoft's data warehouse offerings can take us. Okay, so let's talk for the Microsoft data warehouse and the product positioning. If you haven't seen this triangle before, get to know it well. You're going to be seeing that for the next couple of years, probably. So it's a new marketing thing. It kind of shows, in a way, the positioning of the different offerings for Microsoft, starting, from the lower scale or complexity. As it goes up the scale, it gets more complex, but it gives you, of course, higher availability, higher scalability as far as the data size it can accommodate. So to begin with, of course, we have a very good stack around SQL Server 2008 R2, the standard product that we ship. And as you can see, we expect to cover a large portion of your needs for data warehousing. So this is a number of, we call them data warehousing enablers, that these are features that we added to the product to enable data warehousing in the business. Starting from the Build Faster theme, we added a number of Attunity adapters. Attunity is a third-party company that manufactures very fast connectors to especially Oracle and Teradata. So in SSIS 2008, we ship with Attunity drivers, 64-bit, that they are very, very fast for Oracle and Teradata especially. So if you have data sources like that. Merge SQL statement, it's a new statement where we have insert, update, delete. Now we have merge as well, which kind of combines actions. Pretty much when a key is there, it's going to do an update. When the key is not there, it's going to do an insert. It's called merge. Change data capture, it's another feature we added to enable the ability to capture easier delta changes from an existing OLTP system. It creates actually a separate system table where it does a versioning of the rows, and then you can capture them from there to build up the delta story. And we have data profiling in SSIS. It's one of the tasks that kind of creates a chart and gives you the outliners pretty much of your data very nicely and easily. As far as the manageability, we added data compression and backup compression. Especially data compression gives you, in a data warehouse, easily 50-60% levels of compression savings, both on your I/O storage, plus also on the performance, because since it's compressed, it stays compressed in memory as well. The whole I/O throughput increases dramatically. Because SQL still reads 8K pages, so the more data we can fit in 8K, the bigger chunks of data we can bring back and forth. And again, it stays compressed in memory as well, so we have advantages in memory consumption as well. We support 2 levels of compression, raw and page. If you do data warehousing, 99% you're going to use page compression. And we do have a wizard that kind of gives you an estimate of savings before you do the actual compression, and then you can see which one fits you better. I'm going to go a little faster down here. Partition aligned index views, it's pretty cool as well, because we are aligning the core data with the indexes, and that gives you better alignment and collocation of the data. As far as delivering insights, we have a star join query optimization. So it's not only left, right, inner join. We have star join. The SQL engine recognizes the concept of a star schema, and then when you do joins, it's well optimized on that. Data mining improvements, report builder, where in 2008 it was 2.0, in R2 is 3.0. Is anybody using report builder? All right, a few of you. Do you like it? Yeah? Should we improve it? Sure. It's awesome? We have a biased person on the back. So to do the marketing thing, it included a no charge. Compression, partitioning, advanced security, manageability. If you're looking for improvement, generally the couple of the key improvements we've done is the compression and the partitioning strategies, the way we align partitions with indexes and all that. Those helps tremendously. I'm sorry? The partitioning, yes. The compression, I believe. Enterprise only? Data compression. Backup compression is standard, though. Yeah. I'm sorry? Yeah. Okay, so FastTrack. FastTrack came, you see the arrow, it moves up. So SQL 2008 R2, the base engine, the relational engine, has many, we went quickly through some of the enablers to allow you to build a very decent relational database, data warehouse, I would say up to the scale of several terabytes. Especially if you deploy compressions and partitions properly, you can very easily handle this kind of volumes. Eventually, though, as you're adding more and more terabytes, we talked for that this morning, you're hitting eventually the ultimate threshold of performance, the problem. What is the number one problem? I/O. You're hitting eventually I/O, and what do? Well, you buy the wrong thing. You buy a Superdome, 64 core, and you say my I/O problems are done now, which they're not. Okay, or you buy a Symmetrics, big sandbox, and your problems are still there. Or you buy both, and you have double the problems. So the idea here, actually, I'm kind of preempting my speech, but so leave it where we are. The idea is there is some unbalance we see as we grow and we're hitting some I/O issues or scalability issues. We've seen some reactions from the markets and the companies that not necessarily address the problem right. It's a lot of money spent, so we said maybe Microsoft should sit down with these hardware vendors and with our knowledge on the product and perhaps produce some kind of appliance-like architecture, which we call it FastTrack, to take this guesswork in a way out of the customers. Maybe we do all the work, the testing, and the packaging to guarantee a particular level of performance. So what we see today, based on the service we do on relational data warehouse, we have hundreds or even more deployments, more than a terabyte. Terabyte by now is not a scary thing. Okay? You can go probably down the street with $100 and get a USB 1 terabyte, and there you are. Dozens of deployments or even more over 5 terabytes. So that the sweet spot where we're saying SQL out of the box can handle is already there, this 5 terabyte up to 5 terabytes. So the momentum increases. SQL Server is keep trying to cover the baseline of SQL. We're adding resource governor to manage better, how well data warehouse interacts with the main system. But we needed to go a little further. We needed to give something that is more prescribed and something that is better architecture. So as we're saying today, we see these scenarios, and I have many customers where they're buying a big 64-core system. Oh, this is actually TV. I thought it was screen. And a big SAN. So they're connecting them together. And still, does anybody have that? Have seen that in their companies or customers? Anyhow, big system in one side, big system in the other side, then we're hoping for the best. And they all connect them together. So what's wrong with this picture? The wrong is the system is out of balance. We have a lot of processors, a lot of big SAN, but still something is not right. So the server can today, this kind of server, 64-core server, it's a rate of about 16 gigabytes per second that it can consume. That is the input it can get. So it's like pipes, it's not like plumbing. But the SAN, that SAN in particular, the SAN I have in the picture over there, can deliver only 2 gigabytes per second. So there is a big imbalance between what it can receive and what it can get. So even if the SAN is fully dedicated, which is another mistake, still you don't get what you expect. When you're sizing sometimes systems based on IOPS, IOPS is very good, IOs per second is very important for an OLTP system, like a core banking system, analytic, trading system, things like that. But IOPS don't mean anything to a data warehouse. Because data warehouse is about all what? Sequential scans. We're scanning sequentially, from this point to this point, so it has to be differently optimized. Actually, random I/O is our enemy over here. In this kind of setup we saw before, we have also limited number of controllers, which implies limited I/O bandwidth as well. So what can we do? How can we improve this potentially? Have a balanced system. When we're talking, and we'll talk again and again for the I/O path, let me explain to you a little the I/O path in simple terms. There are the disks in the SAN, the physical disks that they're storing the data. And then you have we call them the server processors on the SAN, that they are typically 2 in an every enclosure, that they take this data out of the disks to be sent out. Okay? And then what we have on the other side, you have the HBAs, as they call them, the controllers on the server. And hopefully there are 2 as well. And those controllers are mapped to cores. So you have the core, the HBA, in simple terms, core, HBA, server processors, and then the disks. So those 4, in a way, is kind of the main elements that they create my pipe. If one of them is not well balanced or well tuned, the pipe assumes the lowest denominator always. If one of them is very small, the whole thing is going to become very tight as well. Did you notice something obvious I didn't mention as an important factor in this pipeline to maximize my data throughput? No? I'm talking for resources.
The number of disks.
The number of disks. No. Memory. For some reason, I didn't say anything for memory. I said how many cores or whatever. Memory is not an issue. So memory is another kind of sometimes dangerous place to go. Say I can add much more memory, and that will improve my I/O throughput. Is that a correct assumption? It is not. It does not improve your I/O throughput. It improves your I/O cache. It's a big difference, because to populate the cache, I have to read the data. So in a proper don't get me wrong, memory will be very helpful for the cache. We need a lot of memory. But that you don't consider it in an I/O sizing and configuration exercise. You have to take the memory out of the picture, the server memory. We'll go to more details on that. So the idea is to design a server and a storage configuration that can deliver all the I/O bandwidth that CPUs can consume. Actually, I should say the cores. So there is a direct correlation between the number of cores and the data the server can consume from the database. Cores, keep remembering cores. Sorry. We don't want to share. I know this is hard to do. It's very tempting and hard to get sometimes, but the storage engine for a large enterprise data warehouse, the storage device should be yours. You shouldn't share with the others, especially the way we plan to configure it. It's very well tuned for the data warehouse. It's not for an OLTP system. We don't need to overinvest on these drives. We'll see for that because our focus is scan performance, not IOPS. We don't need thousands of drives to assume our expectations. Actually, if you go too many drives, you'll be unbalanced in one side. Then you need, I don't know, 1,000 cores on the other side to keep this pipe well balanced. So what is FastTrack Data Warehouse? This is a methodology. It's not a product. You cannot call your sales Microsoft guy and says, I need a FastTrack database. It is SQL 2008 R2, as far as the product is concerned. And the FastTrack architecture is the way you're getting an appliance, a server configured from HP, from IBM, or from Dell, because this is the three vendors that are supporting that, based on the expectation from your side on the terabytes you want to support. We'll go through the menu of options later on, but the idea is, for example, I need a 20 terabyte system. HP or IBM or Dell will tell you, here it is. It's a bomb. Pretty much you can call them and say, I need that, and a big truck arrives with a bunch of things, and you plug it on the wall, and it should be pre-configured based on these approaches we're talking today. If it's not, you do it on your own. Microsoft.com/SQL, please, that's a site you should visit. That's where we have a lot of these architectures is public. A lot of documents are this procedure and methodology is very well documented if you want to follow it. But the bottom line is we're taking a lot of this guesswork out from you, and we're doing all these tests with the vendors to make sure it meets this criteria. So that is what is FastTrack. FastTrack is supposed to host. Let me clarify that because last session I created some confusion. The FastTrack environment is supposed to host only relational database. But the whole BI architecture, it will include, and I expect it to include, analysis services, IaaS, and reporting services as well. The reason, especially for analysis services, I'm pretty big on that, is because analysis services, the cube files, are mostly random I/O access. Not mostly, they are random I/O. So if you put them in a FastTrack data warehouse infrastructure, the cube I/O is going to be terrible because it's all sequential. Do you know which new technology helps typically random I/O quite a lot? Excellent. I have one shirt. That's all I have. So no, it's not going to make it. It's too low ceiling. Sorry. Solid-state drives. So solid-state drives, you hear it, is kind of the new promised land. We think all the I/O problems will go away with solid states. Based on our tests we've done so far, it's fantastic for random I/O, very fast. So cubes, analysis services, TempDB, things like that, solid states, very good. Sequential reads or writes, like transaction logs, or data warehousing environments, still not as good as the regular disks. Still, things may improve, though. OK. So this is a traditional select statement. It's coming, actually, it's one of the queries in the TPCH standard. It's called query number 2. TPCH, is the industry standard benchmark, and they have about 15 queries. So this query, as you can see, has some sums, some averages, some counts, group bys, and all that. So it's a pretty heavy relational query, especially if this one is multi-million or multi-billion tables. So as you can see, the biggest cost, 92%, is about scanning the clustered index. So when you see behaviors like that on your queries, where the scanning is a prevailing factor in the query cost, that is another indicator that tells you FastTrack will help me a lot. So it's not only the size of your data, it's also the query behavior that you're experiencing. You need to do some kind of query plan analysis and see if this is where you are focusing mostly, because scans will definitely benefit a lot from the architecture of FastTrack. So as we said, this is the components we would like to balance, and we'll talk for that how we go through. So CPU, we're saying we need to maximize consumption of the data, and we'll talk for the next slide. The controller, this is the maximum bandwidth to feed the CPU cores. HBAs, this is the aggregate bandwidth. And then we have the switch. This is a SAN. We're assuming always is a SAN. And then the disks. Now, we don't necessarily always assume a SAN. Actually, we're working with HP on a new appliance that is going to have direct attached storage as well. And we've seen some great benefits on that. Actually, I have in my lab a DL785 from HP, and we have 5 enclosures, HP StorageWorks, direct attached to the server. There are 5 PCI cards, direct attached, and I'm getting 5 gigabyte per second throughput, which is amazing. Much cheaper than SAN and all that. We're using the 2.5-inch disk. I don't know if you've seen that. There is a very small, thin disk, 140 gigabyte, 2.5. So we have 200 disks in this enclosure, and things are happy. So we kind of figured we went from 100 disks. So 100 disks would give me 4 gigabytes per second. 200 disks gave me 5 gigabytes per second. You may say, well, it's not a big difference. The price is cheaper, though, because this is 10K drives. The other was 15K drives. So you need more disks, more than better. We do have versions. It's interesting. There is a FastTrack 1.0. We're coming out with FastTrack 2.0, and we'll see why, because we're having more cores now. So we had to rebalance those architectures, put more disks, because we have more cores now in the system. It never ends. So CPU, as we said, our goal is to tune our system so well that we provide to the CPU cores all the data they can consume. But first, we need to figure out how much data those cores can consume. So in the previous query, that was one of the TPCH queries. That was the benchmark we ran. We executed the parallel query with max DOP4. It's nice to put a limit because why did I put 4, you think? What number that potentially represents? You close. The idea is I represent 1 socket. You don't know that, but in my scenario it was 4 sockets, 4 core sockets. So when you do max DOP4, you kind of, I mean, it's not really science here, but in a way you're simulating 1 physical socket. And we'll see why, because socket is part of the equation. As we go through the slides, socket, cores, all this stuff comes into a very simple formula. So I have, in a way, 1 socket with 4 cores. The idea is to push the CPUs to go up to 100%, because we want to see the maximum consumption. And then what we do is there is a calculation here that you can do on your own as well. It's the number of logical reads times 8K divided by the CPU time. That gives me a very important number that says per core consumption of the I/O. And this is very simple to do. As you exercise in your system, you can capture those perfmon counters and come with that rating. Now, we can get a little more sophisticated and exercise our server a little better, not only doing a simple select with counts and averages, but we can add some more complex calculations, hash joins, and et cetera, that it's much more CPU intensive. So complex queries will consume data definitely at a slower per core rate than simple queries, but again, we're looking more on an average consumption. So I wanted to go a little further down because you do the top thing, you leave it up to us. So you can do all these calculations on your own, And in the site I told you, Microsoft.com/SQL, I think we have by now already, there is an Excel spreadsheet where you plug different numbers, how many CPUs you have, your I/O system, and that calculates the per core consumption for you, or you do some stuff manually. But what we've seen, an average on current x64 cores, we expect a consumption of about 200 megabytes per second per core. So keep thinking, left side, right side. What do you like? Probably the cores are right side is the end. Well, that's your left side. So 200 megabytes per core, it's kind of the expectation. So we do use that as the basis of our published reference architecture. This is the start of all the calculations. So keep that in mind. So the CPU core count and the consumption rate of the workload. So again, remember, I have 4 cores and 200 megabytes per second. Okay, so that gives me about 800 megabytes per second per socket system. So that, the number of core count and the consumption rate will determine the number of controllers and the enclosures that I need to provide the aggregate throughput. So I know I can consume 800 megabytes per second. Fantastic. How many controllers I can plug on the other side to bring that in? Balanced. So number of controllers will determine the minimum disk count for delivering the scan bandwidth. If you have 2 controllers, 3 controllers, 4 controllers, that will tell me how many, the minimum I can have. And then be careful also when you're planning the disk capacity. We should have enough room also for TempDB and perhaps for additional maybe staging tables or what have you for maintenance activities. So we do plan, 10 terabytes of database. We need to see, how much we need for TempDB or other environments. So this is a theoretical system. When things work well out of the box, this is per specification, assuming 200 gigabytes per core. So my system here, as you see, let's start from the left, from the server side, and go to the disks. It's 1.6 gigabytes per second, we say server. Why? I have 2 sockets, 4 core each, so that's 8 cores total, times 200 megabytes per second. That is, so 8 times 2, 1.6 gigabytes per second. Okay? So we have 2 sockets. That gives me 2 controllers. 2 controllers, it's 1 gigabyte each. That gives me 2 gigabytes per second. 2 controllers on the server. And then I have 2 HBAs in the middle in the fiber switch. Same performance. And I have 2 enclosures, and each enclosure has 2 service processors, and each one is 500 megabytes per second. 5, so 1, 2. 2 gigabytes, 2 gigabytes, 2 gigabytes, 1.6. And then in theory, every drive I have, let's say for simplicity, only 4 drives. 4 drives in each is 300 megabytes per second, 6, 12, it's 1.2. So as you see, even in perfect theory, based on the spec from the manufacturer, you can see immediately how unbalanced we are. From the disks to the controllers to the HBAs to how much the server can accommodate. Even in perfect scenarios, we still have some bottlenecks potentially somewhere. Okay? So this is the theory. This is the reality. We don't see these high rates, though, so don't expect that. That's nice to have. Do we have an HP guy here? No? They're downstairs. Well, they cannot control that. So you're not going to see any 300 megabytes per second. We typically see about much less. We see about 180 megabytes per second from the disks we see. And generally, we see less. It's not 500, it's 360, and that's not 2, that's 1.4, and all that. So this is the observed scenario we've seen. But the theory over here remains. I still can consume, I believe that's the base of our theory, 200 megabytes per second per core. Keep remembering that. So how that helps me to build a big system. So in this scenario, I'm starting with 2 sockets, 4 cores each. So again, I have total then 2 sockets and 8 cores. Since I have 2 sockets, I'm going to have 2 HBAs. Having 2 HBAs, having 2 HBAs, I'm going to have 2 enclosures. Having 2 enclosures and 4 cores, I'm going to have 4 storage processors. Actually, it's 2 storage processors per socket. Okay? And then you notice I have 4 LANs, not 4 disks anymore. This is more real. I have 4 LANs per enclosure. Why 4 LANs? 4 cores. So the number of sockets will determine the number of HBAs. The number of cores will determine the number of LANs. Every LAN is mapped to a core. Every HBA is mapped to a socket. And this is pretty much the holy grail of the balance system. Which means if all of a sudden I get a new system that has 6 cores, things get out of balance. So let's say I get 2 sockets, 6 core each. What should I change to make it balanced? Everything else. Okay, a little more specific. Should I change my HBAs? I have 2 sockets, 6 cores each. So the HBAs will stay the same because the HBAs are mapped to the number of sockets, the physical. I'm sorry?
How do you measure if you've got a bottleneck in your HBA?
The way you measure it is you have to, the HBA is feeding the socket. So each HBA, it's roughly, depends what HBA you use, of course, but let's assume you're using the 2 gigabyte. So 2 gigabyte each is going to give me 2 plus 2, 4 gigabytes aggregate to pass through.
So there isn't like a per form counter that will say...
No. No, my friend. Hey. No. Well, people try to produce, and feel free if you produce some formula you can share it with us. But this is in the ballpark to remain on the balance side. So the number of sockets, if you increase the number of cores, what are you affecting? The LANs. So as we said, this is how the system Windows and SQL maps a LAN. Every LAN is mapped to a core. And every HBA, it's mapped to a socket. That's how the system works as far as the throughput. So if I would add more cores, I would leave the same HBAs and the same storage processors, but I would add 6 LANs in each enclosure. So I would have 6 plus 6, 12 LANs. So that gives me the balance. If I don't do that, I create an imbalance that my server can consume more, but I don't give them enough from the sun. It's not bad, it's just you're not optimizing. Question? No? Okay. Yes, sir.
That seems to represent 5 lumps on there. Is that just... have I got that right?
Is it 5? 1, 2, 3. Oh. Then I have to fix the slide. Supposed to be 4. So if I add 2 more sockets of 4 cores each, you see I have to double now pretty much the whole. That is the everything story. No? You're getting more HBAs, 4, 8, and then the life goes on. And then if I need to add much more, you get the idea. So for now, to make it simple for your planning and architecture, HBAs should be the same number like the sockets. LANs should be the same number like the cores of the system. And that gives you this balanced architecture between the two of them. The number of storage processors also is important. As you see, we have 2, 4, it's double the number of the sockets. It's very associated to the number of sockets as well. Okay?
What about like the speed of the processors or the technologies that the processors are using?
Absolutely. So what do we do? That's what I said. We have a FastTrack version 1.0. I mean, pretty much when you go to the website, you'll see that we have, This is version 1.0 done 2 months ago with what we have, what we know. Absolutely, this thing changing constantly. Why I'm telling you this theory is you potentially get an architecture I don't even have, we don't have authorized per se. At least this will give you some guideline, I hope, as you architecturing that on your own, you're kind of building your own FastTrack-ish configuration. If you buy from HP or from Dell or from IBM, they'll have this kind of architecture of the time of the day that it was done. Absolutely. If you get faster processors, that may increase the consumption rate. So if that increases the consumption rate, that I may need more even disks or faster disks or whatever. I have to worry for the right side. So they are working now for the version 2.0. Any day now they're going to release it with a 6-core. Of course, by now they're planning 8-core to be released. But this is a 4-core based architecture. We will have a 4-core, a 6-core soon. So this is the estimates again we can use. We have a 200 megabytes per second per core for the load. That equates to 800 megabytes per second. And then we need to figure out also the total bandwidth for the CPU and the storage. So this is the version 1. You may say we have available today. The version 2 will come soon. The biggest one I have is a couple of big ones. Is the HP ProLiant, the DL785, that can go up to 48 terabytes of system. And this is as you can see, this is an 8 sockets, 6-core each, 48 total. And then we have here the number of MSAs. They're using MSA, 15K, 300 gigabyte drives. This is the initial capacity. I would say, I don't know if in theory is the minimum capacity, but I would say this is, to me, would be the minimum capacity to start thinking about that level of configuration. So in a way, there is the 385 is the small, the 585 is the medium, and then you have the 785, which is the large. So these vendors, they're going to have version 1, version 2, version 3, etc. going on. Any questions on that? I don't have the pricing. Okay, you don't ask pricing, so I think list price. Typically, when you're pricing a database, data warehouse, the key factor is how many thousands of dollars is per terabyte, end to end. That's it. If you ever compare with competitors, that's the figure to ask. I believe list price, nothing applies to New Zealand. I don't know how it applies, but worldwide, list, we're looking about 14,000 per terabyte or so for FastTrack, which is a very good number for that. And this is end-to-end licensing and hardware and the whole deal. It's not bad. Actually, it's yes. Yep. That's with the system running and operating and spinning and serving. Yeah, that's hardware, software, setup, the whole deal. All right, so let's talk. So the hardware, we talk for the hardware layout. So HP came, and again, I'm not biased to HP, I'm just referring a name. They plug it on the wall, see prompt flashes, what do you do? So you have to do some stuff. We have the LANs already allocated. And now the tricky part is to create the proper file structure and file allocate, how we spread the files, the database files, across those optimized LANs. We need to stripe them properly. So the way we're doing it is we like to create one SQL data file per LAN for every file group. So in my scenario before, if I have 8 LANs, I want to create 8 data files, one per LAN. How big this data file should be? Actually, when you create the data files, what you should be careful about their size. That all 8 of them should be same size. So be careful to be all same size, so we minimize the round-robin issue, because the way SQL works is when we have 8 data files, for simplicity, if I add 10 records, it's going to go round robin 1, 2, 3, 4, 5, 8, 9, 10. It kind of goes, it crosses, it distributes the data as they're inserted across the available data files. The problem is if all the data files get full and you have auto growth on, one data file, not all 8, one data file will increase by that. So now all the data go there, not to the other 7. So of course the best practices is leave the auto growth on, but get an alert. When you get the auto growth event occur, you need an alert so you go and you size all the data files properly, so you don't have this issue anymore. TempDB file groups, they're going to share something different from the common practices we suggest. Typically, we suggest in OLTP the TempDB to be in its own LAN separate from the others. Here, we found best performance when the TempDB and the data are on the same LAN and spread out actually across the same structures. The reason is a lot of is not kind of overlapping. When you're scanning data, if you have a good clustered index, etc., we don't use much the TempDB. And when you use it, it's kind of exclusive operations per se. We don't use much. That's why it's all scan optimized, the system. Let me show you a little better over here to understand it. So in my scenario here, I have 16 LANs in my example, which implies I have a system of 16 cores. I mean, immediately you can see that if it's well architecture, 16 LANs is immediately 16 cores, which means depending, and you see here the number of sockets comes in place, but we always think in cores, how many cores I have. So when eventually Intel releases one socket 16 core, talking for changing everything. Oh, I know it's coming. I'm sure that would be good for your SQL numbers. Okay, so 16 LANs, 16 data files. Staging is optional. So if I have a staging area where I store data during my ETL, maybe I do 16 data files there as well. And TempDB as well, 16 files across the same LANs. By the way, side note, why we like a lot the HP, the Heaven enclosure is called MSA 2000. It's a very expensive enclosure. The nice thing with that is, by the way, I didn't say that, all the LANs here are 2 drives, RAID 1. Every LAN is 2 drives, RAID 1. And why we like that? Because HP MSA allows dual reads from both drives. Most of the times when you think mirroring, you think the other is the failover kind of standby disk. But MSAs, that's why they're more expensive, they allow dual reads from both disks. So in a sense, you always have all the disks are participating in the reads. It's very, very fast. Log, from all the logs files, we have another LAN, separate LAN. All the 3 databases, we store them in a separate LAN that exists over there. So in simple terms, every enclosure from HP, there are 11 drives over there. So 8 of them are used for the data, 2 for the log, and 1 is a spare, 8, 2, 1. I think I have a picture for that as well. Do I have a picture? I'm sure I have later on. So this is the file layout. You have to do it manually. Okay, that's part of the FastTrack architecture. You get the hardware. Remember, when you plan your file layout of the database, you should follow this architecture to take advantage of this spread. How we spread the I/O. So the scans are quite optimized in SQL Server. The idea here is to tune the scans. We keep scanning. Again, this is large amounts of data that we want the scanning to be optimized as much as possible. That is the big issue over here. So SQL Server issues a large number of asynchronous read ahead when performing scans. So we want it not only to be very efficient when it reads the particular information, but have enough data proximity when it reads ahead. It reads very relevant information to where you're immediately reading. So that's where the memory perhaps comes in play. If you have large amounts of memory, the read ahead can be even larger and gets more data into the cache. So the size of the I/O is dependent on the continuity of these data pages, and we'll talk very soon. One of our biggest things to consider after we finish building the box is to keep it so well tuned. Because what do you do every day? You're kind of fighting with yourself every day. You're doing something that can break all this beautiful picture of continuity. What? You're loading data. You're loading data. So it's not like you're loading it once and everything is happy. Every day you have to load data. And data, by adding new data to your beautiful system, what it can introduce? It can introduce fragmentation. Fragmentation is our biggest enemy of sequential information. So let's see what we can do for that. Actually, here there are some DMVs we're suggesting to show you a little how the read-ahead operations can be determined. So there is the average fragment size in pages, and then the values of the size. So I/O can be multiple of 8Ks up to 512Ks, depending on the fragmentation size. If it's too fragmented, your page size is going to be smaller because it has to read more pages, smaller pages from different spots in the disk. So pretty much in the FastTrack system, you shouldn't have too many indexes as well. Clustered index is going to help you a lot, as you already know, but clustered index introduces fragmentation. Clustered index is very good for pages, they are sorted well, contiguous ranges, but we need to manage the fragmentation. Heap is another good option. You don't necessarily need, heap means I have no index. It's the bare table, and you're loading the data sequentially. So there assumes you're pre-sorting the data, integration services or whatever, you sort them, you pre-sort them as you're loading them, and then when you load them, they are already sorted in a hypothetical clustered key in a way. But there's no actual clustered index in place. The nice thing with that is, again, I don't have to worry much for fragmentation. It's much less. But you need to be careful. You understand there's no index over here in case you need to search for particular values. If you're scanning, it works well. Another thing we can use to maximize the scan throughput is the -e startup parameter. If you haven't seen that before, go ahead and search out there on the internet. -e allows the SQL Server to the page allocation size is bigger. By default, it's 8. I think we can go up to 64 with -e, and in a way, you tell to the SQL Server optimize the page allocation more for data warehouse rather than OLTP, where you like small pages for that. Minimize use of non-clustered indexes. Try to stay on that. Index creation as well. This is also to minimize fragmentation. Max DOP1 and sort in tempdb. Because then it becomes all serial, the creation of the index. It's going to take longer to create the index, but it's very well defragged and well optimized. Volatile tables, like staging tables, they should be in a separate file group or even in a separate database. Why would I do that? Why would I isolate a staging area, you think, in a separate database even? Exactly. To take care of the fragmentation, because staging is going to be very quickly terribly fragmented. You keep adding, removing. I mean, in many cases, I have customers every month, they're dropping that staging database altogether, and they're creating a new database, fresh, out of the box. And periodic maintenance, don't forget that. We may have to rebuild the indexes, update statistics, things like that, to avoid fragmentation. So let me talk a little for the overlapping. We need to be careful a little when we have overlapping batches that they can lead to page splits. So that's why the pre-sorting is very important. When you're loading data, try to pre-sort them and have them in a sorted mode already. If they're not sorted, assuming you have these pages on the top with those keys, 31, 32, 33, 34, 35, and then you're adding a bunch of pages here on top of them, and they go more or less like that. And this kind of assumes you don't even have a clustered index. This one is a heap. So pages, going in arbitrary order. This one is terrible because now all of my beauty things I spend all these weeks preparing, I do a data load one morning, fragmented. There's no ranges anymore. It's all over the place. Okay, it will work. But your performance is going to go lower on that level. So what do we do? Again, we're using heaps in many cases. We can use batch size of 0 as you're loading data. This is great if you don't need parallelism, but of course it's going to take longer. Or what we really prefer is the two-step load. So we're using a staging area, staging table, where we take all the heat of the fragmentations or whatever, But then after doing it over here, after it finishes persisting the data there, then I do an insert select to the target table. By doing that, I don't have this level of fragmentations anymore, especially if I do max DO, PO1 or things like that. This is a very common strategy to avoid fragmentation. I know it's going to take longer. It's like 2 steps, but that's the best way to do that. And even parallel data warehouse, if you ever go to that level, that is the strategy there as well. There is a whole loading node that it receives the data, sorts them right, and then puts them to the right end results. So 2 steps. Bang, bang. I'm going a little faster because I think I'm running out of time. Partitioning, of course. It's a good friend of ours. Don't forget about that. If you can, this is some other ideal situations. If your daily load can fit in one partition, or if you plan your partition that it hosts 1 day worth of data, that's perfect because I can load in the staging table the daily data, and then I can take that and treat it as a new partition and merge it to the existing table. That works quite well. Partitioning is something to consider as well, big time. We don't have time to go through the partitioning strategies, but you can do, merge. You can drop a partition. You can materialize a partition into a table. We have very nice things. If you ever plan partitions in a big table, I highly encourage you, from practice, to make sure left and right you always leave an empty partition. Same process, but it's empty, doesn't have any data. Why? Because we found, especially online, it's much faster to add another empty, and then merge those new tables in one of those 2 empty holders in a way. If all is full, and you add at the end a new partition with data, we've seen locking issues. But if it's already there and empty, it's already pre-allocated in a way the space. So make sure always left and right, you always leave something that is empty. No data. Same structure. Let's say you have monthly partitions. You create a month, let's say whatever you call it. Just leave it there. Okay? Avoid auto-grow. We talked for that. Manually make sure it works. And file groups can help us a lot as well, especially to stop loading for backups. We haven't talked about backups yet. You have a 40 terabytes. How you back up this thing? Or you restore it. Just to focus on file groups, that's another whole section. File groups will help you a lot because we can back up and restore on a file group level. The idea is we have a file group potentially that is my historical archive data. That's where I move eventually some of my tables because it's very easily to alter a table and move it to another file group. And then you can back up this file group or even make it read-only after you back it up. And then, we support restoring a database and gradually restoring its different file groups. A database can be partially available, and then as you're retrieving more file groups, restoring, then more data becomes available. So use file groups for backup and restore management. Simple as that. Okay? That's how you back up the big one. If you cannot avoid it, we need to do periodic maintenance, defrags, and things like that. And then partitioning over here to have some read-only areas to deal with that. If nothing works, what is the last resort? What can we do if the database is terribly fragmented, nothing works? I know it's a big thing to do, but reload. We have to BCP, bulk insert out and bulk insert in. I mean, it's not pretty, but if we don't take care of, every day kind of some of these best practices, it may affect us. So rebuilding indexes with max DOP1 and sorting TabDB, it's really helping you. It really defrags the indexes quite well. It's single-threaded, but it's really the best way. Reorganize works fast, but the actual physical pages, we don't see, still the fragmentation exists. Okay, we reorganize, it kind of cleans up the pointers a little better, makes it more consistent, but the physical layer doesn't really change as much. Okay, this is good if you don't have much time to clean it up.
What about activity database consistency?
That too. It has to be done. It doesn't affect my performance, but this is more database management. The question is, how about maintenance of the database, like DBCC, CheckDB, I'm assuming, and things like that? Sure. Does it affect performance? No. Then it goes to the whole other thing, how you do that. So some other environments, if it's really online, you have to create kind of a DR side. Maybe you use log shipping or something like that, and then you do, for these sizes, for multi-terabytes, you have some offsite that you do it once in a while. Yeah. All right. So this is what we said. Sometimes it's best to start fresh. You can create you don't have really, it's kind of rebuilding, but you can create a new file group with new data files, and it's fresh. And then you can simply copy the table in this new file group. So you can do it slowly or whatever is more highly fragmented. The new file group with the new data files is definitely not fragmented. It's fresh. So that's another strategy to do that. Of course, insert, select, rebuild the indexes, drop them, and all but the final step. Yeah, that's the other thing. All but the final step, dropping and renaming the database, can be done online. So online, we can move objects to other file groups. We can rebuild indexes. We can do insert selects. All this stuff can be enabled online. Of course, that implies Enterprise Edition, but I think we are Enterprise Edition already here, hopefully. So a couple of case studies. This was an insurance claims company. They wanted to load 50 gigabytes in less than an hour and enrich. So this is another thing in your project you need to be careful. They may tell you load the data, and by the way, get some demographics and this and that and this and that. So enriching can add a lot to the data load time. You need to think for that. So what we did is we used the partition destination table. This is the partition strategy I was telling you. It was done by customer key. And then we had as many partitions as the cores. That's kind of another scenario. This is how SQL Server can do parallelism, how you maximize the parallelism without queuing. That's in SQL 2008 R2. Every core can map internally to a partition, and when you do the select, it goes across the partitions, issues multiple threads, and works very nicely. And then we did separate file groups per partition. This is to kind of tune a little better the loads. This is the physical design of these guys. That was a little older than today's architecture. It's a DL580, as you can see. And we have 16 cores. And this is then closures I was telling you that has 3, 6, 12. Actually has 11 drives. And then these are all connected to the server over here. This is in your slides. You can see that later on. This is some of the times we achieved with these guys. It works pretty fast, as you can see. This is one of the existing appliances. I can tell you later on who was that. I'm going a little faster. This is a Korean company over here, telco. And this is where you can use a little NUMA. If you have multiple data files, NUMA architecture, I don't know if you know NUMA. The idea is you can specify a connection to go to a NUMA. It's by different TCP IPs in a way. NUMA is a pair of CPU and memory. So this is really isolated. You kind of having, if you have 8 NUMAs, you have like 8 mini servers in your system. So SSIS supports that. If you do NUMA connections, this is a way, these guys, they did in 16 actually. Very quickly, parallel data warehouse. Massive, big. Let me go to a picture where we can spend a week talking about it. There. Okay. So this architecture, it kind of looks like the FastTrack, but it looks like a big FastTrack. You see the white dotted line on the left? On the left implies this is the network, this is the world. On the right, this is all internal. It's an appliance. It's a big box, as far as you're concerned. The idea is we have a bunch of storage nodes and a bunch of database server nodes. All this stuff is transparent to you. The only thing you're connecting is the top, is the control node. That's where you issue your queries, your data loads, all the processes, and the control node takes care of all. You don't need all this stuff like the FastTrack. It knows how many nodes it has. It knows all the distributions. It's very nice. It's coming out by the end of this year, and it is definitely ranked for the multi-terabytes. I would say 15 terabytes or more. This is something you're looking for. And we support 1, 2, 3, up to 3 data racks in the system. And each data rack is about 80 terabytes, depending on the disk size. So 3 data racks will bring you about 240 terabyte system. Okay? So that's the future. I guess I ran out of time. I can take maybe one question or two. Or you had enough of hardware. Thank you very much for your time. Fill out the evaluations. Thank you.